Good morning. This is Unit 2, Day 6. We're going to look at the graphs of rational functions and how to graph them without a calculator. So we're going to let n of x be the numerator and d of x be the denominator of and be polynomial functions, where d of x does not equal 0. Then the rational function r of x, is equal to the numerator over the denominator. Okay, the domain is always going to be all real numbers except the values that cause us to divide by 0. The domain restriction comes from the values that make the denominator equal to 0. So we're going to find the domain for f of x. It's going to be all real numbers except when the denominator equals 0. This is why I've been factoring. We learned how to factor. We went over factoring because we have to factor this denominator. So I'm going to do this over here. X squared minus 3x plus 2. I know that I need the factors of 2, which are 1 and 2. The factors of x squared is just going to be x and x, 1 and 2. Now, we want them to both be positive or both be negative. Since we're adding to be a negative, they're both going to be negative. And I'm just going to FOIL this quickly to make sure it works. X squared minus x minus 2x is minus 3x. Perfect. Negative 1 times negative 2 is positive 2. Very nice. So now we set each one equal to 0. This is going to be only when x equals 1, positive 1. Move it over, set x minus 1 equal to 0. We get x cannot equal positive 1. We move this x minus 2, set that one equal to 0. This is going to be when x cannot equal positive 2. So my domain had asked me to find the domain. The domain is going to be all real numbers except for 1 and 2. So the way I'm going to write this is the smallest number comes first. So negative infinity all the way to 1 union. You cannot include 1, so no brackets here. I'm picking back up at 1 all the way to my next restriction is going to be 2 union. I'm going to start back up at 2 and I'm going to go all the way to infinity. So this means all real numbers except for 1 and 2. Now right here at x equals 1 and x equals 2, these are going to be vertical asymptotes. So these are not removable discontinuities. These are going to be asymptotes. When x equals 1 and x equals 2. So let's look at the horizontal and vertical asymptotes. The vertical asymptote theorem is pretty easy. It's just going to say x equals a. The graph behavior will approach the vertical line and either increase or decrease without bound. So we're going to go up or go down. So the limit as x approaches a, when the minus sign is on the right of the a, this means from the left. A little minus sign means from the left. And this is either going to go to usually positive or negative infinity, depending on the question. As we approach a, the little plus on the right-hand side of a means from the right. And this is also going to go usually to either plus or minus infinity. So let's look at this actual problem. It looks like my asymptote is 3. My vertical asymptote is when x equals negative 3, because this is 1, 2, 3. And I'm going to write it in over here. The limit, or we would say the limit as x approaches -3 from the left. So remember, the negative on the right-hand side means from the left of your function. I'm not sure what this function is, but I know that the asymptote from the left, so this is the left-hand side of the asymptote, and as we approach it, it goes up to positive infinity. So we can put plus infinity, I don't know. Usually we don't use the positive, we just negative. Now I'm going to do the other side. The limit of this function as x approaches -3 from the right, so this is the right-hand side of this dotted line, and as we approach the dotted line from the right, it goes down. So this is going to be negative infinity. The horizontal asymptote, it's always going to be like y equals, or usually going to be y equals a number. Sometimes going to be y equals a number. The graph of a horizontal asymptote will tend towards this line. It will it'll go to like negative infinity or positive infinity. Let me just change the color. Plus or minus infinity along the line. What this means is this looks like the horizontal asymptote right here. And we're going up towards to the right, so that'd be positive infinity as we get closer and closer to that line. And as we get closer and closer to that line from the left, we go to negative infinity. So the function as x approaches infinity, your y values, it looks like we're going really, really, really close to 1. For your function, as we go to the left, the y values looks like we're getting really, really close to 1 also. So we have an actual a theorem for horizontal asymptotes. It depends on your graph. So if the numerator is less than the denominator, the degree of the numerator, we don't care about the coefficients, the exponent of the numerator is less than the exponent of the denominator, then your horizontal asymptote is going to be the line y equals 0. So this is the x-axis. That will be your asymptote. This is a good example. Let's look at this. Y equals x minus 2 over x squared minus maybe like 6x plus 10. Okay, I just made this up, but the degree of the numerator is 1, and that's less than the degree of the denominator, which is 2. Okay, so this is going to be the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then we use the ratio of the leading coefficients. So ratio, and I'll show you what this means. And it's going to be like A over B. This is the time that we do look at those coefficients. So if we have something like y equals maybe 5 minus 8x squared over 2x squared, it doesn't really matter the rest, I'm just going to write it something, 3x minus 4, okay? Do you guys see that we have x squared over x squared? And those, even though this is not the first term, this is the term with the highest exponent. So this is my degree is 2. And that's equal to the bottom degree. The term with the highest exponent is also 2. Okay. Then since they're equal, then we use the ratio of the leading coefficients. The number directly in front of that x squared is negative 8. And the number directly in front of this x squared is 2. I don't really care about the 5. I don't care about the rest of this. So my my horizontal asymptote will be y equals, and then negative 8 over 2. And we can simplify this. This will be negative 4. Now, the last one says, what if the degree of the numerator is actually bigger than the degree of the denominator? So this is my third case. the graph has no horizontal asymptotes. However, it will have an oblique asymptote. It may have an oblique asymptote if the degree is one more than the denominator. So that an oblique asymptote just means it'll be like a diagonal line or a curved line. It could be a quadratic even. So if we have something like y equals x squared, maybe like minus 5x plus 4, right? Divided by something with just an x, something like this. The degree of the numerator is 2, and that's actually greater than the degree of the denominator, which is 1. So this one, there's going to be no horizontal asymptote. However, since the degree is 1 more than the denominator, there will be an oblique asymptote, and we'll go over how to figure that out. It will become important as we move through our course to be able to analyze functions completely without access to graphing. We're not going to always be able to use Desmos. You should begin by developing some procedural thinking to help you along this pathway. Graph each rational function and analyze. We're always going to have to factor. If they don't do it for you, factor the denominator and the numerator. Okay, so I'm going to go through these one by one. The x-intercepts, we just set the denominator equal to 0. But is 2 ever going to equal 0? The numerator in this case is 2. Does 2 equal 0? No. That means that there's not going to be any x-intercepts. We can put none or... The y-intercepts is going to be when we plug in 0 for the x's, and we'll get the y value. So we'll say f of x is y equals 2 over 0 minus 2 is negative 2, and 0 plus 3 is 3. And this is 2 over 6, or, and there's a negative here, so 2 over negative 6, or negative 1/3, I think, if you simplify that. So my y-intercept is actually 0, comma, negative 1/3. Oops. Pretend like that's a 3, okay, guys? The asymptotes, my vertical asymptotes, this is when we set the denominator equal to 0. And this one's already factored for us, which is really nice. So we're going to say that, well, this is equal to 0 when x minus 2 equals 0. So we're going to move that 2 over when x equals 2. It also happens when x plus 3 equals 0. So we're going to move that 3 over and x equals negative 3. Alright, so my vertical asymptotes are actually these equations. X equals 2 and x equals negative 3. My horizontal asymptote, remember we have this long theorem. If the degree of the numerator is less than the degree of the denominator, we do this one. Equal to the degree of the denominator, we do this one. And if the degree of the numerator is bigger than the denominator, then there's none. Okay, well, let's check this out. It looks like the numerator has 2. This is going to be x to the 0, right? And the denominator, if I FOIL this, we're going to get x squared. Okay, so the degree of the numerator is less than the degree of the denominator. And this means that my horizontal asymptote is going to be y equals 0. The holes would be if I could factor the numerator and cancel with one in the denominator, like there was an x minus 2 in the numerator, I can cancel with this one. Then there would be a hole right here when x is positive 2. But in this case, since there's nothing that can cancel, there's no factoring that is going to cancel, there's going to be no holes. There's no removable discontinuities. So I'm going to put none. The domain, the only restrictions I have is x cannot equal 2 and x cannot equal negative 3, and the smaller ones comes first. So my domain is negative infinity to negative 3, union negative 3 to the other vertical asymptote, which is 2, union 2 to infinity forever. Now, my range is going to be everything except for my horizontal asymptote, and maybe even any holes. So I don't have any holes. All I have to worry about is this horizontal. So it can be everything except for 0. So I'm going to say negative infinity to 0. Use your parentheses. Union. We're going to pick back up at 0 and go forever. Alrighty, I am going to go ahead and graph this for you. Right here at negative 3, there's an asymptote. And at 2, there's an asymptote. And it looks, oh, there's an asymptote right here. So I'm not exactly sure which quadrant they're in. I know what it's going to look like if I can find out which quadrant they're in. So this is what I'm going to do. I'm going to use the interval test. I know that it's going to change right here at negative 3, so I put it here. And it's going to change right here at 2, so I put it right here. Alright, on the left-hand side of negative 3, we need to try something. I'm going to try a negative 4. You can try whatever you would like as long as it's over here. Alright, negative 4, when I plug this in, negative 4 minus 2 is negative 6. And then I have a negative 4 plus 3 is a negative. So a negative times a negative will be a positive, so this would be plus. I can't try negative 3. I'm going to try something in between. I really like to try 0 if I can. This would be in between. So I'm going to try 0. I tried negative 4 right here. I'm going to try 0. If I plug in 0, I'm going to get 0 minus 2, which is negative 2. And then 0 plus 3 is 3. This would be a negative number. So 2 over a negative number, this would be negative. And then I have to try something on the right-hand side of 2. I'm going to try 3. 3 minus 2 is positive, times a positive, and then a positive. So this is going to be all positive. So if it's positive, it's above this x-axis, it's going to look something like this. If it's negative, it would be a u, but since it's negative, we're going to make it an upside down u. Something like this. And then the positive means it's going to be in this quadrant. These are negative numbers, so I have to put it up here, and it's going to look something like this. So this is the graph, and I don't even have to use my calculator to graph this. So when we're trying to find the x-intercept, we set our function equal to 0. That only happens when the numerator equals 0. So we have 2x minus 1 equals 0. That since they're factored for us, we can set each one equal to 0. X minus 2 equals 0. And when I solve this, I'm going to add 1 to move it over. 2x equals 1, divide by 2, x equals 1/2. And also I'm going to move the 2 over, adding it, x equals 2. So my x-intercepts are going to be at 1/2, 0. Yep, positive 1/2, 0, and 2, 0. So it is going to touch the x-axis this time. It's going to touch right here at 1/2 and at, but actually I can see that this is x minus 2 over x minus 2. This is not going to really be a x-intercept. This is going to be a hole. Since we can divide them out, this is going to be a hole. This is where the hole is going to be. So this is going to be my only x-intercept right here. Alright, my y-intercept is when I plug in 0 for everything. So what I can do is divide these. This is going to be my whole. I'm not going to forget about this. But my function is actually going to be y equals 2x minus 1. When I'm done dividing them, this is what's left over, 2x minus 1. So I'm going to plug in 0 for x. 2 times 0 is 0. We have y equals negative 1. This is going to be my y-intercept. This is at 0, negative 1. So right here. Alright, and this is a straight line, so that's really all I need for my straight line. This is going to be it. Something like this. But we're going to have a hole when x equals positive 2. So we're going to have a hole right here. I'm going to actually just like circle it. We'll find out where it's at. Give me a second, I'll find out where it's at. So my vertical asymptote is when our denominator equals 0, but since we're actually since we can divide these, there's going to be a hole right here instead of an actual asymptote. So there's none. The horizontal asymptote is we're going to be able to use our theorem, but since what's left over is just a straight line, we don't have a fraction on what's left over, there is actually not going to be any. We don't have a fraction. Sorry guys, there was an announcement. Okay, so the hole, let's find out where this hole is. I know this is when x equals 2 because we set this term equal to 2. You can say either one equal to 0, and we found out x. This is when x equals 2. Now we're going to plug it into what's left over to find out what the y value would be. So 2 times 2 is 4, minus 1 is 3. So the hole should be at 2, 3. So the graph should actually go through this point right here, 2, 3. Alrighty, the domain is going to be all real numbers, except again, wherever that hole is or asymptote. So it's going to be negative infinity to where the hole is, and then also pick back up to infinity. The range is going to be all real numbers except for wherever that hole is. So the y value is 3. So I'm going to say negative infinity to 3, union 3 to infinity. Now I'm going to go over the limit and slant asymptote, what happens when it's not factored for us. I want you guys to actually try this one. This one's not going to give you one, but I want to go over, why does it keep on happening? I want to go over 4. I think this one would be a little bit more difficult. So our first step is that we need to try to factor this. So number 3, I tried to factor the top, but it didn't work. I couldn't factor it. So what I'm going to do is I'm going to divide it. Since the x squared has a degree 1 more than the denominator, x to the first power, then I'm going to divide it, and this is going to have an oblique or a slant asymptote. And I'm going to show you how to do this. So remember, I just changed the sign, and I put the 2 in the house, and I just put the coefficients of the divisor, the dividend on the top, and then I'm going to bring down the first number. This is 2, and then we multiply it. 2 times 2 is 4, and then we add. Negative 3 plus 4 is positive 1, and we multiply it times 2 is 2, and 5 plus 2 is 7. So my slant asymptote is going to be y equals, and this is 2x plus 1. Oops, plus 1. I already had the 1 here, sorry. So 2x plus 1. My vertical asymptote is going to be where the denominator equals 0, and this is going to be when x is positive 2. So we're going to put x equals 2, and that is going to look something like this. And then on my, we're just going to graph a line. So we usually start at the y-intercept, which is positive 1, and then we use the slope. We're going to go up 2 over 1, up 2 over 1, just keeps on going. And really we just need 2 points to draw a line. Kind of wanted to see what it looks like. Oh, this is a dash. Sorry. This is the asymptote. Alright, I can't factor it, so there's not going to be any holes. I can't divide anything, so there's no holes. The x-intercepts. The graph is going to look something like this. So there's no x or y-intercepts on this one, but this one is going to be something like this. So I got to actually set this equal to 0 and find out where the x-intercepts are. So I actually tried, since I can't factor the numerator, I tried the quadratic formula, and this is actually not going to have any x-intercepts. So I'm going to put none, doesn't touch the x-axis. It could have right here, but it doesn't. So the y-intercepts is when we plug 0 in for each of the x's. So this will be term will be 0, 0. We have a 5, and then we have a 0 minus 2 on the bottom. I'm going to put the negative out in front, and then we always put 0 first. So I'm going to make an order pair, 0, comma, negative 5 over 2, which is like 2.5, negative 2.5. So that would be something like right here, and this will go down also. The domain are the x values. It's going to go infinitely to the left and infinitely to the right, but there is an asymptote right here. So my domain is going to be negative infinity until the asymptote, which is at 2. And then we're going to use our parentheses. We cannot include 2. We're going to do union, gets very close. We're going to pick it back up at 2, and we're going to go to infinity. The range on my y values is not going to go any further up than this 2.5, but it goes down forever. So that's negative infinity all the way up to 2.5 or negative 5 over 2. Let me just use what I have right here, negative 5 over 2. So you guys remember where it is. This right here, negative 5 over 2. Union, and then this one starts way up here, and what we'd have to do is find this point. I found it. It is 12.48 all the way to infinity, the end behavior. So usually we're using like limit notation, or we say like as x goes to the left, what happens to my function or my y values. As x goes to the right, what happens to my y values. So as we go to the left, my y values go down to negative infinity. So this one's going to be negative. As we go to the right, my function goes up to positive infinity. So this one's positive. Alrighty, this is the last one that I'm going to do today. If you try the other ones, if you have any questions, please ask me. Have a great day.